Okay, so we're going to look at the next unit, which is an application of equilibrium to acids and bases. So there are actually three different ways to define something as an acid or a base. We're going to only use one of them. The first theory, the one that you're probably first introduced when you find out about acids and bases, is actually called Arrhenius Theory. And Arrhenius Theory looks at whether something has an H plus or an OH minus. So anything that's an acid, for example, H plus, HCl, that would give me H plus when it dissolves in water. So that means that HCl is acidic. Likewise, with an Arrhenius base, if I take something like sodium hydroxide and dissolve it in water, I get sodium ions and hydroxide ions. So in order to be an acid, you have to have an H plus. In order to be a base, you have to have an OH minus. So this is the most limited definition of acids and bases. The second category, or second theory of acids and bases is Brønsted-Lowry Theory. And this is the theory that we're going to use as we examine acid-base equilibrium. So Brønsted-Lowry Theory defines acids and bases in terms of H plus transfer. So a Brønsted-Lowry acid is a proton donor. A Brønsted-Lowry base is a proton acceptor. So we're looking at an H plus transferring from one molecule to another molecule. So in Brønsted-Lowry acids and bases, we always have pairs of acids and bases. So we never have just an acid, we always have an acid and a base paired together, which we will look at in just a few minutes in a little more detail. The third definition of acids, which we're not going to spend a lot of time on, is called Lewis theory. And Lewis theory looks at acids and bases in terms of electron pairs. So because it looks at electron pairs, it is the broadest of the theories. And this explains anything that is acidic and anything that is basic. And here you can see the definition: electron pair acceptor, electron pair donor. So like ammonia is an electron pair donor because when I look at the Lewis structure for ammonia, it has a pair of electrons that can bond to something else. A positive ion or a metal ion would be an electron pair acceptor because obviously it has a positive charge. Okay, so now let's look a little more at Brønsted-Lowry theory of acids and bases. So this is looking at HCl. So here's my HCl right here. And here's water. So what is happening is the H is coming off the HCl and being transferred to the water molecule. So according to Brønsted-Lowry theory, HCl is the acid because it's donating this H plus. Water is actually acting as a base because it is accepting that H plus. Now when we look at the products, one of the products is the hydronium ion. And this is actually the way H plus exists in water solution, in aqueous solution. So you can pretty much substitute H plus for hydronium if you rewrite the equation. So if I want to rewrite this with just H plus, this would be HCl yields H plus plus Cl minus. For the rest of this unit, we are not going to really look at H pluses by themselves, but we're going to look at H plus if it's in solution as hydronium ion. So if we have a solution that has hydronium ions in it, it is acidic. This is definitely an acidic solution if I produce hydronium ions. Now the other thing you'll notice is that hydronium could donate a proton to Cl minus, making hydronium acidic, and Cl minus would be acting as your base. So whenever we look at Brønsted-Lowry acids and bases, we look at something called conjugate pairs. So HCl and Cl minus are a conjugate acid-base pair. HCl is the conjugate acid, Cl minus is the conjugate base. The same thing with water. Base, and this would be the conjugate acid. So everything is paired up in Brønsted-Lowry, and every reaction is simply a transfer of an H plus from one substance to another, which makes the stoichiometry really nice because it's always 1 to 1. When we look at ammonia, this explains why ammonia is a base, and you do need to know that ammonia is a base, because ammonia, if we look at that, NH3 does not have OH minuses in it. So according to Arrhenius Theory, it should not be a base, but it is. And this is what happens when I put ammonia in water. I get NH4 plus and OH minus. So now the water in this case is acting as an acid because it's donating one of the H's. Ammonia is acting as a base. When I come over to this side, hydroxide is a base and NH4 plus is an acid because NH4 plus and NH3 are a conjugate pair. Ammonia is the conjugate base, ammonium is the conjugate acid. Likewise, in water, in this situation, water is acting as an acid because it's donating a proton, so that's the conjugate acid, and the conjugate base is OH minus. So just as when we have hydronium ions in solution, we have an acidic solution. When we have hydroxide ions being produced in solution, that is a basic solution. So the first thing we're going to look at is what happens when we put a substance in water. Is it acidic, is it basic, or is it neutral? So we're looking at the interaction of that molecule with water itself. Okay. Besides our standard acids, we also have something called carboxylic acids. A carboxylic acid is an organic acid. And it has this functional group attached to it. And you can see on each of these molecules, there's your COOH group. So, if it's an acid, it must donate a proton. And the proton that gets donated is this one that is attached to the oxygen. So it does not lose the proton that's attached to the water, to the carbon over here. It loses the proton that's attached to that oxygen. We also have organic bases. Amines are organic bases. So whenever you see a nitrogen, that is going to mean that that's an amine and that's a base. So that nitrogen makes it a base, that nitrogen makes it a base, and in this case, this is called a nitro group. A nitro group is not basic, but this is your base. So let's look at just this one because it's sitting right here. And I'm going to draw it like this. So that's another way. This is a benzene ring. These are two different ways to draw a benzene ring. So if I wanted to draw the conjugate acid, this is the acid form. This is the base form. So these two are conjugate pairs. That ammonia, that nitrogen, excuse me, has a lone pair of electrons on it. So it will accept an H+. So when I'm looking at organic bases, you're looking for a nitrogen. Okay. And you'll notice in our examples, water acted as an acid and as a base. So that is called amphiprotic or amphoteric. Those are two words that mean that it can act as either an acid or a base. Water is not the only substance that is amphoteric or amphiprotic, but it is the most common one. And we're going to look at that more when we look at pH. So, looking at the Brønsted-Lowry definition, in this first example, H2S, if I look, H2S over here, HS minus over here. H2S lost an H+. So this would be the acid, which means ammonia must be the base. So here's my acid. That means this is the conjugate base. Ammonia is basic, remember that, which means ammonium is the conjugate acid. Now when I come down here to the second one, I have OH minus and dihydrogen phosphate ion. Well, if I look, the dihydrogen phosphate ion is giving up an H plus when it becomes a product, so that's an acid. Hydroxide is a base. Just like ammonia is always a base, hydroxide is always a base. So when I look at conjugate pairs, hydroxide and water are conjugate pairs. Water would be the conjugate acid of hydroxide. And then my other conjugate pair are these two. This would be the conjugate base of dihydrogen phosphate. Hydrogen phosphate is the conjugate base. Dihydrogen phosphate is the conjugate acid. Okay, we are not going to do this part omitting water. It's a lot easier and a lot more consistent if we always write something dissociating or ionizing in water if we include the water molecule. So we've already seen this one, so I'm not going to write that again. Remember, acetic acid, that's the H that's acidic. If I write acetic acid like this, then this is the H that's acidic. So on the reactant side, I'm going to interact with water, and acetic acid is going to give off the H plus, and that gives me acetate and hydronium. So this is acidic because I get hydronium. If I wrote acetic acid like this, the equation would look like this. Okay, so what you're looking for is an H plus. So ammonium, we looked at that one with the ammonia, ammonium. We would just write that reaction backwards. Aniline, this is the one that I drew for you that is the organic acid. So I have C6H5NH3 plus in water. Okay, since NH3 plus, remember, for a base, the H goes on the nitrogen. This nitrogen is what makes this a base or an acid. So this is the acid form. This would be the basic form. And we're not really going to worry about that one. We can look at that in class if you're really interested.